I'm going to go through a Coulomb's law calculation that's a bit more complicated than the one from the first video. So I got to set up some charges, set the scene for you. So I'm going to set up 3 charges. So let's see, what to call them? Oh, I know. How about charge 1? Charge 2 and charge 3. Yeah, I'll get creative up in here. So remember that Q is going to stand for charge here. And these are all in a line, right? They're 3 collinear points. So if I'm going to be using Coulomb's law here, that needs to know charges and distance, I'd better supply that information. So let's go ahead and label the distances. We could say that this distance here is 0.30 meters, and this is 0.20 meters. Okay, so this whole thing, it's half a meter across, and this one is slightly off to the right. And let's go ahead and label those charges. So negative 8.0 microcoulombs. Okay, so obviously negative charge, microcoulombs, because that's generally the order of magnitude for static charges that you're likely to encounter. That's going to be quite a shock right there, actually. Let's say charge 2 is going to be positive 3 microcoulombs. Now, I know that ordinarily when you leave a number without a sign, it's assumed to be positive. But because charges come in positives and negatives, if I don't put a sign on there, it kind of just looks like a magnitude. And I want to specify that it's positive. And the last one, let's let that be negative 4.0 microcoulombs. Okay, so the point of this problem is to see all the different forces that are acting on a given particle. So let's just focus on charge number 3. What are the forces acting on charge number 3? So here's where we get to something. This is actually a word that we had back when we were doing light and waves. And it's a concept called superposition. Okay, and superposition is where 2 things just add up. So let me put that in like a little thought bubble there. Just trying to cram that in frame without taking up this space, which I need for work. Okay, so the idea is charge 1 exerts a force on charge 3. Charge 2 exerts a force on charge 3. The total force on charge 3 is going to be the combined total of the forces from the other 2 particles. And actually, I could write it kind of like this. The total force is going to be equal to the force on 3 that 1 gives it, plus the force on 3 that 2 gives it. Now, this is an equal and opposite scenario because it's forces, which means that this doesn't have to be the force that 1 puts on 3. It's also the force that 3 puts on 1. This is the force that they put on each other. Okay, this is the mutual attractive or repulsive force between charges 3 and 2. Okay, so if you remember using subscripts way back when we were doing momenta, putting a number below something, just like Q1 and Q2, that's supposed to indicate, oh, that's the charge that belongs to charge number 1. Well, this is the force that belongs to or pertains to charges 3 and 1. It's an interaction. Okay, now we just have to set up Coulomb's law, but with the appropriate values in there. So let's do the force between charges 3 and 1 first. Okay, so that's going to be K times the charge of particle 3 and the charge of particle 1 over the particular distance between 3 and 1 squared. You see, I've just kind of like slapped a 3 and a 1 on everything that can have, they can belong to something. K is a constant, so Q, Q, R, they all have to belong to one of the charges. Okay, so let me just fill that in real quick. Let's see. So K. Good, I just want to make sure that fits in. 9.0 times 10 to the 9th. Newton meters squared over Coulomb squared. So there's K. Q. All right, so the two charges would be 4 times 10 to the negative 6 coulombs, and it didn't make that fraction bar long enough. 8 times 10 to the negative 6 coulombs, and R. Okay, so 1 and 3 are separated from each other by 0.5 meters. Okay, now you may have noticed I don't have any negative signs here. This one is supposed to have the negative sign, so I could just stick a negative sign in there. But look, you guys, we've been struggling with negative numbers ever since we were like in 3rd grade. You know the multiplication rules for negatives. As long as you get the right magnitude at the end, whether the force is negative or positive, I mean, look, we don't think of forces in terms of positive and negative. We think of them in terms of attraction and repulsion. As long as you just get the right number and then you remember what direction it should be, I mean, that's good enough. But if it's bothering you, I'll stick a negative sign in there just for you. Okay, so this all works out to, if you do the math, 1.2 newtons. It's pretty strong. Okay, so that would be the force. Now, what direction is it pointing? What direction is that going? Since these are both negative charges, that's actually a repulsive force. Wait a minute. A magnitude of 1.2 and a direction. What kind of mathematical concept has a magnitude and a direction? That's right, a vector. This is supposed to be a vector. But wait a minute. You can't add a vector and a scalar. They both have to be vectors, which means they're all vectors. Everyone's a vector. And similarly, if that's a vector, what over here could possibly be a vector? Tell you what, I'm not going to tell you. I'm going to let you take a guess at that. Email me what you think. Which of these terms could possibly make sense as a vector? You can't add a vector and a scalar, but you can multiply a vector and a scalar. This is all multiplied together. One of these is a vector. Maybe you can tell me which one. Okay, well, I did the force between particles 1 and 3. Now I got to do the force between particles 2 and 3. So it's going to be here. Let me put a little border on here to delineate this. You know what? I'm going to use a different color. Remember when I had like a whiteboard and a whole bunch of markers? Man, I bet all those markers are dead now. That's sad. It's really sad. Okay, so now that that's all bordered off, let's do the other one. So I'm just gonna fill in the numbers, and you'll get the idea. Force between particles 3 and 2 is equal to K times a charge of 3 times a charge of 2 over the distance between 3 and 2 squared. Right. So if we fill all that in, here's K. Yeah, I'll put the units on. I usually skip units as a convenience, but like, you know, gotta crawl before you walk. Okay, yeah. So charge 3 was that -4. Charge 2 is this +1. And the distance between them is only 0.2. Okay, so even though 4 times 8 is greater than 4 times 3, we're dividing by the square, and dividing by a smaller denominator is actually going to have a effect on the magnitude. When you work this out, it turns out to be 2.7 newtons. It's more than twice as much as that because it's closer. Okay, so this is a repulsive force. This is an attractive force, which means by superposition, let's just put charge 3 right here. All right, here's Q3. It's got charge 1 pushing it away with a force of 1.2 newtons, but it's got charge 2 pulling it in with a with a force of 2.7 newtons, right? So that means that all in all, these sum to a single force pointing in of 1.5 newtons.